Swayam Prabha. Digital India. Educated India.
In the last session, we have seen that it is possible to neutralize the unbalanced forces produced in one reciprocating mechanism system, maybe an engine, by arranging a number of such identical systems in a suitable manner. The basic principle of this type of arrangement is that the unbalanced force produced in one cylinder can be neutralized by that in the other one. So, apart from inline engine, another popular arrangement with reciprocating or slider crank arrangement is V-twin engine. It should be also remembered that though we are referring to these systems as engines, they can be compressors also or can be other types of machines also. In V-twin engine, the two identical cylinders, they rotate a common crank both the connecting rods are of length L, identical. The crank is a common crank. This is the common crankshaft, and of course, these are the common cylinder piston systems or sliders. Let us call this as cylinder 1 and this as cylinder 2, the center lines of the two engines. For the whole engine, of course, this is the main center line which is bisecting the two center lines of the two cylinders, and let us call this as the y axis and this as the x axis, where this angle is alpha, and since it is symmetrically placed, this will be alpha. And we call the angle made by the crank, common crank, with this x axis or the engine center line is theta, and as it happens, this is rotating at a speed omega. The common crank pin is say A, and this one we can call B, and this point we can call C. Now, when this runs, then we know that this particular cylinder or this particular engine will generate an unbalanced force in this direction, which we call F1. And as you know that for all slider crank arrangements, the unbalanced force after the rotating unbalanced part is taken care of course, by a counterbalance, the reciprocating mass produces an unbalanced force along the center line of that arrangement. So, similarly for cylinder 1, this will be the direction, and for cylinder 2, this will be the direction for the unbalanced force produced too. And they of course will have both a primary component and a secondary component. we know that the primary component for this cylinder arrangement will be m reciprocating omega square r into cosine angle made by the crank from the center line. So, it is only this much, and that is theta minus alpha. The secondary component will be lambda twice this. Similarly, here F2 primary will be along this, magnitude at this instant will be, and angle made by the crank from the center line is theta plus alpha, and the secondary one okay. Now, if we want to find out the resultant unbalance along x and y, then what we have to do? We have to take the x component of this primary, add that to x component of this primary, that will give you the engine's total unbalance force in the x direction, in the primary one. So, therefore, F x primary will be nothing but F 1 primary, and component along this of any force along this will be cosine alpha, and we have to add the x component of this force, which is again and the secondary and the y component will be the y component of this force F1, which is F1 p sine alpha, minus the y component produced by F2 So, if we expand this, what we will get? This will be m reciprocating omega square r cosine alpha, and what remains inside is cosine theta minus alpha plus cosine theta plus alpha, and further expansion of this leads to 2 m reciprocating omega square r into cosine square alpha cosine theta. Because sine theta sine alpha term cancels, and here in a similar way we take this common, and inside we have cosine and expanding and simplifying. So, the whole primary unbalance, as you can see, since theta when it is rotating with a constant angular velocity, and if we consider that theta t is equal to 0, the common crank was aligned with the x axis, then theta is nothing but omega t. So, it is a harmonic function of time, that means a fluctuating unbalanced force in the x direction, and in the y direction there is again the unbalanced force which is also fluctuating with the same frequency. Now, you can see that there can be one special case where 2 alpha is equal to 90 degrees. So, this is called 90 degree V engine. In that case, what happens? Your f x p is equal to simply and f y p So, it is very interesting to note that the resultant unbalanced force for a 90 degree V twin engine is nothing but a force which is rotating along with the crank. That means, if this primary force, this is the x axis and this is the y axis, and we see that the resultant unbalanced force at any instant F p, this angle is theta, and it is rotating the same speed along with the crank, real crank or actual crank. So, since the unbalanced force is represented by a rotating force, it is very easy to balance it by putting a counterweight in case of 90 degree V twin engine. So, at least the primary is completely taken care of. If you now consider the secondary, then secondary force in the x direction will be F 1 s cosine alpha plus F 2 s, and this is equal to lambda m reciprocating and expanding, you will find we get finally and the y component I can skip this, but for the sake of completeness, so again for a 90 degree engine, we find that means when 2 alpha is 90 degree, f x term becomes 0, f x s is simply 0 and f y s is root 2 lambda sorry. So, in case of this particular engine with alpha equal to 45 degrees, f x s is 0 as cosine 90 degree is 0 and the y component exists and it is a harmonic force and which is fluctuating at a frequency twice that with which the crank is rotating because it is 2 omega t. Now, to balance this secondary force, of course, then we have to take help of some active balancing system. Maybe we can indicate it like this. This is the plane containing the two center lines and obviously this is the axis of the crank. So, here what we do, we attach a gear to the main crankshaft and then two gears, they are all helicoid gears. So, that when this rotates like this, they rotate like this and obviously this will rotate like this. So, this rotates with a speed 2 omega here, the diameter of the two gears are just exactly half, whereas this rotates to speed omega. Now, we have placed two unbalanced masses in such a manner that when theta equal to 0, that means when the common crank is along the x axis, then the two masses are here. Now, since it is rotating at double the speed, the angle they will make with this direction will be 2 theta in both the cases, and the amount of unbalanced force they will generate if the two masses are lambda by 4 root 2 m reciprocating and r, this is a r. So, this force both of them will generate. So, it will be lambda m reciprocating omega square r, this 4 cancels because this is 4 omega square and multiply by 2. So, here will be 1 2 and the original unbalance produced by the two engines is the same again. And here of course, this component will be sin 2 theta and we already know sin 2 theta. So thus, at every instant, the force developed in the engine can be balanced by the two centrifugal forces rotating in the opposite direction at every instant. Now, the arrangement of V, since the objective is to pack as many cylinders as possible in as small a volume, that gives the maximum power density of an engine. So, there are arrangements in which V's are placed on line. So, we will not discuss that, but I will just indicate how the arrangement is. So, there will be a common crank or crankshaft, and this will be one V, then there will be another V, then another V, like that. So, each V will have two engines or two cylinders, and these V's will be placed in inline condition. So, as in the last session I showed that for a 6-cylinder 4-stroke cycle engine, it is possible to arrange the firing order in such a manner, that means the crankshaft will be of such shape that the primary and secondary both forces and moments, they are completely balanced among themselves. So, here also you will find by suitable arrangements such an engine, maybe it will be 8-cylinder engine, each V will have 2 and there are 4 V's. It will be possible to completely balance up to second order the unbalanced forces and moments. Next, we will take up one more type of arrangement which is fundamentally different from these two, and which at least had substantial importance in the aviation industry in the past. The next we take up the cases where the arrangement is such that the cylinders or cylinder center lines are placed radially in the form of a star. It will look like this. So, there will be 1, 2, 3 and so on, and all these will drive a common crank, and these are the pistons of the various engines. And this is the common crankshaft, this is the common crank, and obviously all the connecting rods will be of identical length, and all the pistons are also identical mass and so on. And of course, here this crank is rotating in this direction with an angular velocity omega. Now, such engines are generally used for aviation industry, that means for driving the propellers of planes. So, being that the situation, two things happen. One is that RPM with which these engines rotate or run, they are much higher than many of the stationary IC engines. Secondly, that since such engines are used for aeroplanes, one has to be more careful and in design more perfect, and so therefore we try to balance even the higher order unbalanced forces, higher harmonics. In IC engines we are satisfied when only up to second harmonic, that is the secondary, the unbalanced forces were neutralized. In these cases we would try to see if it is possible to neutralize even the higher harmonics. Now the problem can be solved both analytically and graphically. So we will be satisfied if we can take any one of these two methods. I will use the graphical method to analyze the situation of unbalance or balance in a star engine, or these are called star engines also, or radial engines. Now before we can do that, we have to develop another technique which is quite useful, and this technique is called the method of direct and reverse crank. Now we have seen that the unbalanced force produced by this reciprocating mass, all the time we have to keep in mind that the rotary part is being balanced. The unbalanced force which it generates has all the higher harmonics, and we know that the unbalanced force in this direction F can be written as the first harmonic, that is primary, second harmonic, this secondary, and so on. That means we know this is, say, m reciprocating omega square r cosine theta plus A2 m reciprocating cosine 2 theta plus A4 like this. All the higher harmonics are present, and this can be represented in another way. What we can say that this primary is produced by the centrifugal force produced by two unbalanced masses, both equal, m reciprocating. So they will produce how much? They will produce m reciprocating by 2 omega square r, and this component will be cosine theta of that. Similarly, this centrifugal force will be m reciprocating by 2 omega square r into cosine theta. So the resultant force will be this one. Similarly, for higher harmonics we do the same thing. What we can say that the secondary, if we consider, and we put here, say, A2 by 4 or 8 m reciprocating at this r, and they are rotating at, of course, double the speed, and this angle is 2 theta, this angle is 2 theta. So the force in this direction will be how much? It will be A2 by 8 into m reciprocating 2 omega whole square into r into cosine 2 theta, and same thing here. So therefore together they will produce So this way all the harmonics or these simple harmonic forces of different frequencies can be thought of to be produced by two unbalanced rotating masses rotating in the opposite direction, and they are placed in such a manner that their inclination is either this or accordingly the twice or 4 times of the crank angle. And so therefore this is a completely hypothetical situation, and here these cranks are of course the direct crank, and this is rotating in the opposite direction, it is called reverse crank. And as you can see, the direct crank and reverse crank should be always mirror image about the center line of the particular engine or particular cylinder. So this way, now we can imagine that the whole actual machine has been replaced by only the corresponding direct cranks and reverse cranks. Now all the direct cranks are rotating in one direction with speed omega, all the not omega, that one primary direct cranks are rotating with omega, secondary with 2 omega, and so on, and reverse cranks are rotating with similar speed but in opposite directions. Now let us see if we apply this technique to this machine, what will happen. I will draw it. First, another thing we have to keep in mind, that here the firing order, if you have n cylinders, and let us consider 4-stroke cycle, then firing takes at what angles? At 4 pi by n interval. So if this is the first, this is the second, this is the third, this is the fourth, and say fifth, say 5 cylinder, and let us also have a 6 cylinder. There are two cases. Let us study this situation. This is 1, 2, 3, 4, 5, 6. Here it is 1, 2, 3, 4, 5. 5 cylinders, and there we have 6 cylinders. Now let us see a very interesting thing. Here we have the common crank. Here also you have the common crank. So this is the direct crank of the primary of all the cylinders, because that always matches with the actual crank, and actual crank is same for all the cylinders. Now which one fires first if it rotates in this direction, say clockwise? So let us see firing order. First one fires. Now what should be the angle between two consecutive firings? 4 pi by 5. So 4 pi by 5 means this one. Next one, when this comes here, the piston will be at the topmost position and there can be firing. So 3 will fire. Next, when it goes to this, another 4 pi by 5, then again the cylinder will be topmost position with maximum compression situation and there can be firing. So then 5, then again 4 pi by 5, so it will be next 2, it will come here and again 2 will fire, and then again 4 pi by 5, so it will come to 4 and this will fire, and after this is over, then again it will go to 1. So a complete cycle of firing is there. If it had been 2-stroke cycle, what would have happened? Then after 1, 2 would have been fired, 3 would have fired, 4 would have fired, 5 would have fired, and then it would have completed one cycle, because the consecutive firing angle would have been 2 pi by 5. So here there is no problem, but here let us see, if it is 2-stroke cycle engine, no problem, 1 will fire, then 2 will fire, 3 will fire, 4 will fire, 5 will fire, 6 will fire. Whenever crank arranges itself along that particular center line, that engine will fire. and it will complete one cycle in 2 pi rotation. But if it is 4-stroke cycle, what will happen? The angle between consecutive firing will be 4 pi by 6, that is 2 pi by 3, that is this one. So first this will fire, then this will fire, then this will fire, then again this will fire, this will fire. So you can see that 2, 4 and 6 are never getting a chance to be fired if we have to maintain firing at equal intervals of time. So therefore, one thing is very clear, that if we use 4-stroke cycle engine, the number of cylinders should be odd. If it is odd, then there will be no problem in getting all the cylinders fired. So with even number of cylinders, alternate cylinders do not get a chance to be fired if we want to maintain equal angle between the firing, to maintain the uniformity. So therefore, in general we will find in radial engines we have odd number of cylinders. That is something which you have to keep in mind. Now let us see, if we have, with the help of one example, let us do say 5-cylinder engine. We will not take up 2-stroke cycles because they are not generally used. So let us plot, let us see the direct cranks of primary. Primary unbalanced. So direct cranks. So you know the direct cranks are nothing but the actual crank. So for cylinder 1, cylinder 2, cylinder 3, they are all direct crank is the same. 1, 2, 3, 4, 5. Reverse crank. Reverse cranks are nothing but, we have seen, just the mirror image of the direct crank about that particular cylinder center line. So for cylinder 1, since it is along the center line, so this will be the position for the reverse crank. Now of course you have to keep in mind that the direct cranks are all rotating at the same speed because they are all primary in this direction with speed omega. And here they are all rotating in the opposite direction with speed omega. Now where will be the reverse crank of cylinder 2? Now direct crank being here, reverse crank will be definitely its mirror image, that means along 3. So this will be the reverse crank of cylinder 2, because here it is the direct crank is here, so reverse crank will be just mirror image. For 3, the mirror image will be along 5. For 4, it will be again along this 2. And for 5, this is the direct crank, so reverse crank will be along. So the reverse cranks of these 5 engines or 5 cylinders we can do if the direct cranks, which is the actual crank at a particular instant, is say at 1, then all the direct cranks are here, and the reverse cranks will be the mirror image about the particular cylinder's center line. So since the direct crank is like this for all the cylinders, for cylinder 2 the reverse crank will be the mirror image of this, so it will be along this, so it will be like this. For 3, if you draw, you will find that its center line is bisecting this angle, so this will be reflected here and 3 will get here. Similarly 4 and 5. So these are the reverse cranks, they are all rotating in the opposite direction at the same speed omega. Now if we place how much mass we have to keep, it will be m reciprocating by 2. So 5 of them, so it will be 5 m reciprocating by 2. So, the centrifugal force produced in this direction will be 5 m reciprocating omega square r by 2. On the other hand, when we place half m reciprocating here, half m reciprocating and so on, then these centrifugal forces produced by these imaginary masses, they neutralize amongst themselves. Thus, so the only remaining primary unbalanced force is 5 by 2 m reciprocating omega square by omega square r, and that can be balanced by placing a counterweight just opposite the actual crank. Now, this is okay. Now, if we consider the second harmonic, then we will have the situation like this. Now, let us consider the second harmonic, secondary. The direct cranks how they look like. For one, the angle made by this when it is here is 0. So, 2 into 0 will be 0. So, the direct crank of cylinder 1 will be the same. For 2, what is the angle made by this? It will be 1, if we call this as 1 unit, 1, 2, 3, 4 unit. So, twice of that means 8 unit. So, it will be 1, 2, 3, 4, 5, 6, 7, 8. So, the direct crank of cylinder 2 will be here. For 3, it will be 1, 2, 3 unit as the theta. So, 2 theta will be 1, 2, 3, 4, 5, 6. It will come here. For 4, it is only 2 units. So, it will become 4 units. So, it will go here. And for 5, it is 1 unit. It will be twice because it is the secondary. Sorry. So, now you see that if we place, how much mass we have to place? A2 by 4, A2 by 8, and this is R. Same here, same here, same here, same here. And this is the direct crank. They are all rotating in this direction at speed omega. So, the centrifugal force produced by the eccentric masses placed at the crank pins of the direct crank of direct secondary cranks, you can see they are balancing amongst themselves. If you now see the reverse cranks, for first cylinder it is the same reflection because the crank is along the so it is here. For 2, the direct crank is here, so reverse crank will be here. For 3, direct crank is here, so reverse crank will be here. For 4, direct crank is here, so reverse crank will be here. And for 5, this is the center line, and the direct crank is here, so reverse crank will be here. And all these reverse cranks, they are rotating at the same speed. Sorry, this is 2 omega, 2 omega. And if we now place again A2 by 8 m reciprocating at each crank pin, so the centrifugal force produced by the masses attached to the reverse cranks, they also balance among themselves. So effectively it means that the secondary is balanced. Following the same procedure, if we now take the fourth order and find out the direct and reverse cranks, you can find out that the situation that whether both the direct and reverse cranks indicate a complete balance or not. So this way you can find out the balancing situation of an engine with multiple cylinders placed or arranged in the star formation, and this is a very convenient way of finding the balancing situation. Theoretical method is also there where you can get all the results together, but I think this will be good enough. And here we also get some physical insight of the whole thing. It will be a nice exercise for one to really see that in which level we first get the unbalanced force present. So you will find that for n cylinder engine up to n minus 1/8 harmonics will be balanced, except of course the primary, because you remember the primary direct cranks are all aligned and that centrifugal force can be easily balanced by a counterweight. So after that primary is taken care of, then up to n minus 1/8 order unbalanced forces will be all neutralized among themselves. So I think this is a situation which we really wanted, that even the higher harmonics are balanced, because aeroplane engines need to be far safer, they should be subjected to lesser vibration, and this kind of more rigorous condition is essential because the speed of operation of these radial engines is generally much higher. So I think we will stop here. We will not go into more complicated situations, and like say there are cases where the rotors are flexible or similar things, we will not go into it. And radial engines, IC engines, these we have seen what is the situation. We have also seen how we can actively attach some mechanism to an engine to produce unbalanced forces which can balance or neutralize the unbalanced forces of the original engine. We have also seen that what is the importance of firing order, and lastly we have also seen that in case of radial engines with 4-stroke cycle operation, we must always have odd number of cylinders if we want the firing to be uniformly placed and all the cylinders are to be fired.